Example 4 is another classic problem of optimization. This is where we take and balance two different competing pathways and optimize for either cost or time or something like that. In example 4, it says, a power cable is run from an offshore wind turbine to a power plant. The turbine is 5 miles out to sea and 7 miles along the shoreline from the plant. Assume it costs $60,000 per mile of laying the power cable on land and $90,000 per mile of laying the power cable in the water. How should you run the power cable to minimize cost? Let that idea sink in. We have an out to sea wind turbine. We'd like to connect it from the sea to the land and then run it along the land until it hits a power plant. Here's what the picture is going to look like. I'm going to draw the wind turbine here. I'll just draw that as a circle. It's out to sea. So let's pretend we have a shoreline that I'm drawing here in black. And we have a power plant that's along the edge of the shoreline. Now, as power cables go, we want to use straight lines. We want to take from the wind turbine to the shore and then to the power plant. You can go straight down and across. You can go straight through the sea, or you can do a combination of going through the sea at an angle and then across to the power plant. We want to minimize the cost. You can see that the cost is going to be a combination of the cost of the cable run through the sea plus a cost of the cable run along the land. Let's set that equation up. The cost of the cable is going to be the cost of the cable on land plus the cost of the cable on water. Now the cost of laying the cable on land is $60,000 times the amount of miles that we laid the cable on land. The cost on the water is going to be $90,000 times the number of miles that we laid cable in the water. We want to come up with an equation where our variables are involved in the miles on land and miles in water, and then minimize using derivatives. Let's go back to the picture. In the problem itself, it said that the wind turbine is 5 miles out to sea, and once it hits the land, there are 7 miles between it and this plant. So 5 miles from the shoreline to the wind turbine, and then 7 miles from this point over to the power plant. Hopefully you notice that we've created basically a right triangle here. We're going to utilize that right triangle. Here's how we do it. The key thing here of this right triangle is we're going to call this little value between the 90-degree angle and the path that the actual cable takes. We're going to call that value X. That's the easiest way to do it. There are other ways of doing this, but that's the one that's going to be easiest. Once I call that my variable X, then the amount that we travel along the shore is 7 minus X. So the amount that you travel along the shore is 7 minus X. And if we call the hypotenuse of this right triangle Y, then the amount that we've traveled through the water is Y. Notice that in this case, Y is going to be the hypotenuse of the right triangle whose legs are 5 and X. That means you can find Y by taking X squared plus 5 squared equals Y squared. Since we have a right triangle, the Pythagorean theorem works, and therefore the miles that we travel along the water is going to be the Y. The miles we travel along the land is going to be 7 minus X. Let's plug that into the equation that we've created. Just as a little aside, I want to once again emphasize my equation is X squared plus 5 squared equals Y squared. We want to solve that for Y, which means Y will be equal to the square root of X squared plus 5 squared. Y here is the miles in the water. So I take this cost equation and I simplify it. I'll write C for cost. 60,000 times the miles on land. We know that the miles on land is 7 minus X. Plus 90,000 times the miles in water. We know that the miles in water is Y. If I want to write that in terms of X, that's going to be square root of X squared plus 5 squared. This is an equation that I can find the maximum of. Let's get rid of that here. I'm going to apply the techniques of derivatives to be able to do that. Before I start taking derivatives, let me multiply and simplify and rewrite this so it looks a little bit nicer. My cost function here, 60,000 times 7 is 420,000 minus 60,000 times x plus 90,000 multiplied times x squared plus 25 to the 1/2 or 0.5 power. We use exponents instead of square roots because it's easier to take derivatives in this form. I multiply the 60,000 through because it's easier to take derivatives in this form. Now I can look for critical values of this cost function by taking c prime. The derivative here, derivative of 420,000 is 0. Derivative of minus 60,000 times x is negative 60,000. Plus derivative of this portion, we're going to have to use a chain rule to do that. That means I take the exponent and I multiply it times the piece in front. 0.5 times 90,000 gives me 45,000. The inside function stays the same. And I reduce my exponent by 1. If I take 0.5 minus 1, I get negative 0.5. Now at this point, the chain rule then says multiply times the derivative of the inside function. The derivative of the inside function is 2x. That's my derivative of the total cost. If I want, I can rewrite this. It's a little bit nicer if I rewrite this. The 2x multiplied by 45,000 is going to be 90,000 times x. Instead of writing this as x squared plus 25 to the negative 0.5 power, I think it's going to be easiest to see this as dividing by a square root of x squared plus 25. Hopefully that makes sense. Critical values happen when this is 0. Therefore, let's set 0 equal to this whole expression. At this point, we want to solve this equation so that we can get the critical values or critical value. By the way, I didn't say this earlier, but it is important at this point that we had the positive square root, and we know we can use the positive square root because we are talking about how many miles. And so it would not make sense to have traveled a negative miles. But that is very important here when we're solving this, because if you used a negative square root, none of this is going to work out very well. Okay, so how do we solve this? There's a number of different ways. I always start by adding 60,000 to both sides. And then we have a choice. If you read along in the book problem, at this point, they square both sides. I'm going to do one other step before I square both sides. I'm going to multiply by this square root on both sides. That's going to give me 60,000 times the square root of x squared plus 25 equals 90,000 x. And now I'm going to square both sides. Again, you didn't have to. Actually, let me do one more step. Since 60,000, since I can divide both sides by 60,000, I guess I'm going to go ahead and do that and make my life a little bit simpler. Divide both sides by 60,000. You end up with the square root of x squared plus 25 equals 1.5 times x. Now I'm going to square both sides. Again, the book squares both sides at this stage, and that's perfectly fine. Just if you square both sides at this stage, you're dealing with pretty big numbers. So it's a little bit easier to square both sides at this stage. If you square both sides here, you'll notice that you get x squared plus 25 on the left-hand side. Hopefully everybody understands what we're saying there. We take that, square the left-hand side, take that, square the right-hand side. And on the right-hand side, 1.5 squared is 2.25. And then the x becomes squared. Let's subtract 1x squared from both sides. In other words, subtract x squared from both sides. Now you can clearly see we're trying to solve for x. And how to do it. 25 is equal to, when I subtract x squared from both sides, I get 1.25 x squared. Then take and divide both sides by 1.25. We end up with x squared equals 20. And because we're talking about a value, I can take the positive square root of both sides. In other words, if you go back to that picture, it's pretty clear x has to be a positive value, and the square root of 20 is approximately 4.47. So technically x should be the square root of 20, but that's approximately 4.47. Moodle's going to ask you for the answer rounded to 2 decimal places. So that's a long solving process, but it comes down to the fact that we can take a derivative, set that derivative equal to 0, and solve this equation to find a critical value. That critical value comes to be square root of 20. If you wanted to figure out the minimum cost, all you'd have to do is plug in square root of 20 into this equation here. But that's not what the question asked for. The question asked for how many miles on land should you run the cable, and how many miles on water should you run the cable. Let's check out the land mileage. We just found this x. Therefore, if you're running your cable on land, you take that 4.47 that you just found, plug it in for x. 7 minus 4.47 would give you 2.53. That means you should run the cable 2.53 miles on land. On water, you should run the cable whatever you get when you plug in and solve for y into this equation. Let's do that algebraically. Algebraically, the miles on land, 7 minus x. We now know that x is about 4.47 or square root of 20. So the number of miles on land is 2.53 on land. So about 2.53 miles on land. If you wanted to be more specific, it's 7 minus square root of 20 miles on land. Miles on the water, well, remember, miles on the water is given to you by this equation. All you would have to do is compute that. If we take square root of 20 and then square it, oh, that didn't work. Well, let me replace the x with the square root of 20. There we go. 5 squared is 25. Square root of 20 squared is just 20. So that becomes the square root of 45, which is approximately 6.71. miles through the water. And there you go. This is an approximate too, to be precise. That means we run the cable on land for about 2.53 miles, then shoot out into the water, and at the angle we'd go to the wind turbine, it would be about 6.71 miles through the water to reach the wind turbine. That's how this problem is done. Again, this is a very classic problem. You can minimize a lot of stuff, but it always has the same type of drawing, where we have some portion on land, some portion in water. The water value we can find using the Pythagorean theorem. The land value we can find using the remaining land piece after we cut off the x. The key there is, again, setting this value as the x. As long as you set this value as the x, then things fall into place, right? And then everything should work out numerically. So that's how to do this type of optimization problem.